So hello, here we have an industrial robot, a bioreactor and a factory. One might wonder what do they have in common? They all speak OPC UA, the open communication protocol for the industrial Internet of Things and Industry 4.0. What if our digital models also could speak OPC UA? So hello everyone and welcome to this webinar again, connecting digital models with industrial devices using the OPC UA library. My name is Otto Tronarp, and I'm a developer at Wolfram Core in the System Modeler team, where I mainly work with the development of the System Modeler product itself. However, sometimes, like here with the OPC UA library, I do get the chance to be a user instead and use it for developing model libraries. So in this webinar, we will explore what OPC UA is, how we can use it to connect Wolfram System Modeler and our digital models to industrial devices, and some use cases that it unlocks. So OPC UA, Open Platform Communications Unified Architecture, or OPC UA for short, is an open standard for machine-to-machine communication that was initially developed for industrial automation. It's developed by the OPC Foundation and was initially released in 2006. It is the successor to the classic OPC standard designed to overcome its platform and security limitations. So with built-in support for encryption and authentication, it is secure and reliable. And in contrast to its predecessor, OPC UA is cross-platform and scalable, meaning it runs on most common operating systems like Windows, Linux, and Mac OS. And it's scalable in the sense that it can run on anything from cloud servers down to small embedded system and even microcontrollers. Much of this is thanks to it being based on existing internet technologies that are available in most platforms. So at the core of the standard, we have an information and modeling framework, as well as services for browsing and accessing data, and other services for receiving data and event notifications. The information modeling framework is object-oriented and includes constructions like hierarchical composition, object types, and type hierarchies. It makes it possible to standardize information models for industrial equipment and increases interoperability. All the services in the standard are defined in an abstract way and are then mapped to existing communication protocols. This makes the standard very flexible in that it's easily adaptable to new communication protocol as they emerge. So for example, mappings to WebSockets and MQTT has been added after the initial release of the standard. So standardized information models for various industrial domains are published separately from the core standard and are called companion specifications. So here we have a few examples. We can see a large automations presence in energy, building, factory, and process automation. However, there are also representatives from very different domains like mining equipment and laboratory and analytical devices. In all, there are over 60 published companion specifications. So what if System Modeler and our digital models also could speak OPC UA? Let's look at some potential applications. So we could do a data collection and analysis. So here, for example, we have a lab scale bioreactor, a device made to support a biologically active process. Maximizing the yield from these kind of processes requires good control over the environment conditions like temperature, pH levels, oxygen levels, and many other parameters. By connecting to it, we can collect the data that is relevant for our particular process and do post-processing in Wolfram language. We can also do various kinds of data analysis or create data-driven models, like, for example, use the data to train a neural network. Which brings us to the next use case, high-level control and user interfaces. So what's the point of training a neural network unless we can put it to good use? So we can take the trained network and import it into System Modeler With our model running in real time and connected to the system, we can feed sensor data into the neural network and use the output to control the system, thereby running the neural network against the real system in real time. We could also prototype and develop other high-level algorithms for controlling our system and run them in real time against the real system. Another option is to build dashboards and custom operator interfaces using Wolfram language. This can be extremely useful, for example, in lab settings where we might do a wide variety of different experiments using the same equipment. Then you can build tailor-made control panels that are targeted to the needs for operating and monitoring your specific experiment. Another broad area of applications are digital twins, software in the loop and hardware in the loop simulations. So say we're writing PLC code to control our system, and we want to test that PLC code before deploying it to real hardware. If we have the model of our system running in real time, we can connect that to our PLC simulator. Then we can run the software in the loop simulations and test our PLC code before deploying it to actual hardware. Likewise, when we do deploy our PLC code to real hardware and connect that to our simulation, we can run hardware in the loop simulations, enable us to conduct more tests without access to the real system. If the human-machine interface, the user interface of the system, is connected using OPC UA, we can also connect it to our digital twin instead and do operator training with the real operator environment, or using the real operator environment, which could be a cost-efficient solution since there is no wear and tear on physical equipment and no downtime in production. It also enables safe failure simulations for practicing emergency procedures without risking actual equipment or production. So for connecting system modeler and system modeler models to OPC UA servers, we have the Wolfram OPC UA library. It is available to system modeler users as a free download from our library store. And the library enables real-time data exchange with an OPC UA server by providing components for reading and writing node values. It uses the efficient TCP binary mapping of OPC UA with TCP IP as the underlying transport protocol and the binary encoding for message content. So it's highly efficient with minimal overhead and low bandwidth usage. It also has support for security features like authentication, message signing, and encryption. So if we look at some of the components in the library, we have at the core of the library, we have the client component. This component represents the connection to the server. So here you can specify connection parameters like the server URL, what authentication to use. It supports username and password-based authentication as well as certificate-based authentication. And you can also configure the security setup where you want to have everything sent in plain text or sign your messages or sign and encrypt everything. All components for reading and writing data must have access to the connection to the server, so they need to be connected to a client. And the client is also used to distribute the clock signal that triggers the read and write request. So we connect the clocks that define these clock signals that are then distributed to the connected read and write blocks. It is, of course, possible to have several instances of the client component, so you can connect to multiple OPC UA servers from the same model if that is required. OPC UA uses X509 certificates for secure communication and enabling encryption, authentication, and trust between clients and servers. That is likewise most commonly known HTTPS as well uses the same kind of certificates. So it's a well-established technology. Each of the OPC UA applications, server and client, has one application instance certificate. There are two major ways to manage your certificate. One can have self-signed certificates, or one can have certificates that are signed by a certificate authority. So with self-signed certificates, they are generated by each OPC UA application, the server client. And the trust is explicitly configured, meaning each application must manually trust the other's certificate. And this becomes quite cumbersome in large systems when you have many clients and many servers. So all clients need to be configured to trust all the servers that they need to communicate with, and all the servers need to be configured to trust all the clients that wants to communicate with them. On top of that, certificates usually have an expiration date, so it becomes difficult to manage in large systems. A better option then is to use a certificate authority. So one have certificates that are issued by one trusted certificate authority that establishes a chain of trust. So the trust is implicit. Each application trusts the certificate authority, and therefore any certificates signed by the CA, which makes it a lot easier to manage in larger systems. So there are specific components for reading and making read and write requests, and they are available in variations for working with values of type real, integer, and Boolean in the shapes of scalars and 1D arrays and two-dimensional arrays. Common for all the read and write components is that they have parameters for specifying which node ID to read from or write to. And as I mentioned before, they must also be connected to a client block for getting the connection to the server. In OPC UA, nodes are identified by either a numeric integer ID or a string identifier. One thing is that OPC UA has a richer list of types than Modelica that is used in System Modeler. So for example, it has unsigned and signed integer in all combinations of the usual width variants, whereas in Modelica we only have one basic integer. So when writing data, we must also specify the specific OPC UA data type that should be used for the write request. So how does this scale if we increase the number of nodes that we want to write data to? So when we connect the write component to the client, all those writes are aggregated into one write request, meaning the overhead of adding an additional node to write to is minimal overhead, so it's fairly efficient. And the same holds for all the read requests. So all the reads are aggregated into one single read request that is executed with the clock frequency defined by the clocks connected to the client. In some cases, you might want to sample different nodes at different rates for various reasons, and there are special components in the library for facilitating that use case as well. So let's move on to error handling. In OPC UA, status codes are used for indicating the state of a request and the quality and state of a data value. So status codes comes in 3 different severity levels. They can be good, uncertain, or bad, and they can also carry additional information about the reason why the status isn't good. For example, maybe the value is at the limit of the sensor operating range, or the communication with the data source has failed. So all the components for reading and writing values have one extra output, which is the severity of its current status. They also have a parameter to control the block's built-in error handling, where the possible choices are error on status severity uncertain and bad, which means the simulation is aborted as soon as something isn't good. Or we could have error on status severity bad, which means the simulation continues with uncertain values, but aborts when we have bad values. Or we could simply do reporting of status changes. So the simulation continues regardless of the status. So selecting any of the last two options mean that we could do error handling in the model. Maybe the bad value isn't that important to our operation, or we can shift to a different operating mode to remedy the situation. To aid in the decision making, the components also come with timestamp outputs, so that it's possible to take different action depending on how long the value has had the current status code. Another effect of selecting to only report status changes is that the simulation will automatically reconnect to the server in case of the connection goes down due to network issues. So let's jump into System Modeler and do a quick demo of the library. So this is System Modeler, and here to the left we have the class browser that shows the loaded model libraries that we have. And here we have the OPC UA library loaded. Included in the library are several examples that we see here that illustrates different concepts used in the library and different usage scenarios. To make it easier to get started, the library is shipped is bundled with two OPC UA servers. So we don't have any dependency on, so the examples doesn't have any dependency on an external OPC UA server. So the first one is the example server, which contains nodes of all types that's supported by the library and is used to support the examples provided in the library. But you can also use it for your own experiments. The other server is more configurable. So here you can create the server with a custom list of nodes. Yeah, so the var server serves a custom list of variables of type double. So it's real valued nodes only. But you can define your list of nodes yourself and use it for your experiments. So we're going to use that for this demo today. So there is a link that leads to the location on disk where we can find the actual executable for the server, and we have to then go into the actual folder for our current platform. So I will start the server with two variables, one called the ref and one called level. So now I have started that server. Now I have prepared a model of a tank that is controlled by a PI controller that reads its reference value from the OPC UA server and reports the current tank level to the OPC UA server. So we are going to build a small example model that sets that reference value and reads back the resulting tank level from the OPC UA server. So let's create a new model. So the first thing we need is a client that we can drag in here. And in the client, we have various parameters for configuring the connection to the server. So the first most important one is the endpoint URL, which is the URL of the server. The default value will work for my example server here. And here we also have the security configuration. So we could select between unsecured communication, meaning it's not encrypted in any way or not signed, or we can select secure communication, and configure it, opening the editor for that. And here we can set up all the various security parameters, like selecting the algorithm for signing and hashing, and the security mode if you want to sign the messages or sign and encrypt and so on. And there are options for whether you are using self-signed certificates or CA-signed certificates. In this example, though, the server doesn't have any security enabled, so we need to have it in unsecured. So the next thing we need is to define our clocks for reading and writing. And for that, we're using the standard library components in clocked and clock signals, where we have a periodic exact clock that we're going to use. So we will use the same clock for reading and writing. So I will connect that to both the clock inputs of the client. And we will set the clock rate to 10 milliseconds. So next, we wanted to write to our server. So we go to the OPC UA library, and in components, we can find, if we dig down, a sub-package with components for real signals. So it's organized by the type. So we have real signals, integer signals, and Boolean signals. So we're going to drag out the scalar write block, which we will rename to write ref, so we recognize it. And we will connect that to the client. So we need to configure our write block. So first of all, we need to select the type of the variable that we are writing to. And as I mentioned before, the types in this bundle server is only serving double values. So we will select double. And it uses, then we will specify the node identifier, pointing out the exact node that we want to write to. And first we need to specify what type of ID we are going to use. And this bar server uses string IDs. And we named the variable ref for the reference value for the controller. Then we also need to specify a node namespace. Usually that is for all the local server nodes, that is 1. So that is correct in this case as well. So there we have our write block. Now we need to provide some signal to write as a reference signal for the controller. And for that, we will use a signal source from the standard library in the blocks package. And there we have sources, and we will use a pulse source for this. So something is happening. We'll connect that to our write component and set some parameters. So I want the amplitude of the pulses to be 0.25, and the period we can set to 20 seconds. And let's set the offset to 0.25. So we will get the pulse train alternating between 0.5 and 0.25. Next, let's read the the level that the current level that the simulated plant model publishes to the OPC UA server. And for that, we will use a read block, of course, reading one scalar real signal. And we start by renaming it to read level so we can recognize it. And connect it to the client. Next, we need to, so here is the difference between the read and write, or one difference between the read and write block. When we write, we need to specify the type for writing, but reading, that is not necessary. It will be automatically converted to the Modelica type from the originating OPC UA type. But we once again need to set the node ID type to string ID. And the node ID was level. And again, the namespace is going to be 1. So that's everything you need to do for reading and writing two different node values. So let's validate the model to check that I didn't make any mistakes. And that looks good. Next, we need to set up our model for real-time simulation. So we go to our experiment setup. And it doesn't make sense to have an end time, so we will set this to infinity, the stop time. And we will also check the synchronize with real time to true. And that's everything set up. Now we will switch to Simulation Center, the environment for running simulations in System Modeler. And here I have the pre-built simulation for the plant model that I will start. That will start writing data to the OPC UA server. And we can look at the current tank level when it's running. So no one is providing any reference. So the reference is set to 0, and therefore the tank is empty. So if we build and simulate our model that we created, the read and write, we suddenly start seeing changes to the tank level, which is because we are now providing a reference input. So if we create a new plot and look in our model, so we had the write ref that writes the reference signal for the controller. And we can plot the U variable there, which is the input to it. We can see the signal that we provide to the controller. So we can see the pulse train here alternating between 0.5 and 0.25. And here we have the read block that we named read level. And if we look at the output Y from that, we could see what result we get from the simulated plant model. And here we see that when the reference starts to go up to 0.5, the tank starts to fill up and we have some overshot before the regulator gets it to the reference value. And then when the reference changes back to 0.25, the controller regulates it back to that level, and so on. So that's how easy it is to build a simple model for reading and writing data to an OPC UA server. So let me stop these so I don't consume too much CPU. and switch back to the presentation. So to summarize, the Wolfram OPC UA library is built on an open and evolving standard that provides secure and real-time data exchange with a wide variety of physical systems. It enables applications like data analytics, software in the loop and hardware in the loop testing, and operating training, and much more.